So today's lesson is a follow-up to yesterday's lesson where we introduced you to simple harmonic motion, the idea of an oscillating mass on a spring moving backwards and forwards, and how that resembles circular motion. And you'll remember that we talked about how that relates to frequency and to period. Today we're going to extend upon that and relate this to some other concepts in the unit. We're going to talk about energy in simple harmonic motion using our elastic potential energy formula that we saw a couple of days ago. So you'll remember that elastic potential energy has the formula and is equivalent to 1/2 kx squared, where k represents the spring force constant, or the spring constant, and x represents the distance or the displacement from the equilibrium position, which is the rest position for that spring mass system. So let's just remind ourselves about how elastic potential energy relates to the spring and the mass. So if I have a mass right here attached to a spring, and we're going to assume right now that as I've written it, that the mass right now is kind of sitting at equilibrium, at its equilibrium position. So at that point, the value of x is going to be 0, or 0 meters or 0 units of distance. But what I'm going to do is I'm going to take it and I'm going to stretch it out. So we're going to imagine that I've taken that and I've stretched it out. Now I could also have compressed it. And then so what I've done here is I've moved it a distance from that equilibrium position out a bit. And so my value of x now is not going to be 0. It's going to have some sort of value relative to the rest position. And so when I move that mass from the rest position outward or inward, I can stretch or I can compress, then there's some elastic potential energy stored within that spring. Right? If it's not in motion, then it's not possessing any kinetic energy. But the moment I release that spring that has been stretched or compressed, then the mass starts moving, gains velocity, which means that some of the elastic potential energy is going to get converted into kinetic energy to help it move back, and it's going to want to eventually, due to friction, move back to that equilibrium or rest position, provided I'm not interacting with it. So in this case, we're going to call x A. And A, I think, is a good word. We can also call x A, because A, of course, relates to the amplitude if we were to think about that as a wave. So our whole unit has been thus far about energy, and so, of course, the law of conservation of energy needs to be considered when solving problems related to simple harmonic motion, because we have a spring, so there's elastic potential energy. We also have kinetic energy because the spring mass system is going to be in motion potentially, and we also may have to consider gravitational potential energy if we have a vertical system. So we can say, for example, in the horizontal system that I just discussed, we could talk about there being elastic potential energy and kinetic potential energy in varying proportions throughout the motion of that mass spring system. So going ahead and substituting in the equations for elastic potential energy and kinetic energy respectively, we can come up with a new formula that we can call total, that represents the total energy of the system. Now, of course, we may again need to consider other energy forms, provided the situation. We might also have to consider gravity and its part in the whole thing. So here is a problem that I'd like you to try. First, I'd like you to write it out and then give it a whirl on your own. See how whether you can navigate through it, formulating a plan to solve the problem given the information at hand. And if you are struggling or when you're ready to verify your solution, then just resume the video. So I'm going to just develop a picture here. I'm going to read out the problem. So as it stands, the question is, a 55-gram box is attached to a horizontal spring of force constant 24 newtons per meter. So I'm just going to draw that out. I'm going to imagine that there's a spring here, and at the end somewhere I have some sort of a mass. And then it says it's compressed. So I'm compressing that spring 8.6 centimeters to the left of the equilibrium position. So I'm going to consider, as I've drawn it here in blue, to be my equilibrium position. And I'm going to go ahead and I'm going to compress it. So I'm going to draw my, as though that I've compressed it. Here it is, my in green. And at this point, my value of x is 8.6 centimeters, right? And then what it says, what I'm going to do, it's going to be released. So, you can envision now that this, mass is going to, has some elastic potential energy, so it's going to move back and forth, it's going to oscillate. And so the question is, what is the speed of the box when it is a position 5.1 centimeters from the equilibrium position? All right. So I know this is a conservation of energy problem. So my initial energy has to equal my final energy. So I'm going to refer to that as ET and ET prime. And so thinking about the forms of energy that are relevant here, I have elastic potential and I have kinetic in varying amounts throughout the motion of that spring mass system. So EE prime and EK prime at the end. So I'm going to substitute in the formulas for each of those. And I think it's just a good form to include all the relevant forms of energy, even though their values may be zero, either at the beginning or the end, or anywhere in between during a motion. It's important to include them all. You never know when something might pop up that needs to be included where you maybe didn't know it was needed to be included before. So I have kx squared over 2. I'm going to call that kx1 squared over 2, which means that this x that I'm talking about, the 8.6 centimeters, happens to be x1. So that's my initial kind of compression or distance displacement from that equilibrium position. And then I have my mv squared over 2. I'm going to call this v1 in that it's the initial velocity. All right, so moving on. I also have my kx2. And so over 2 and my mv squared over 2. So, presumably this is going to move a little bit and it's going to be at a spot where it's only 5.1 centimeters it's not saying to the left or to the right, but I'm going to assume it's just to the left of that equilibrium position. So let's talk about this. So I know that initially my velocity is going to be 0. And how do I know that? Well, over here I had compressed and was holding this mass in place. So that allows me to kind of eliminate this whole piece, because if V1 equals 0, then that whole term is gone, right? So that certainly simplifies things. Another thing is that I notice that I have dividing by 2. All of these terms are being divided by 2, so I can really just pull out the 1/2 as a common factor and get rid of all of those 2's. So I'm going to go ahead and substitute in my values. So my spring constant was 24 newtons per meter. And then I have my x1, which was 8.6 centimeters, so dividing that by 100 to get it into meters, 0.086. It's getting a little squishy here, and I'm not going to forget to square that. And that's going to be equal to, and I'm running out of room, so I'm going to just kind of move this over a bit. My 24 times my x2, and x2, and that should be squared, 0.051 squared plus, and the mass of that spring was 50 grams, I believe. Let me just double, 55 grams. So that means that I'm going to divide that by 1,000. So 0.055 times my V2 squared, this V2 right over here. Okay, and so then I have a one variable linear, quadratic equation, and I can solve for V2. When I solve for V2, I should get that the velocity is 1.4 meters per second. So if you did not get that answer, but your process was right, then double check your algebra. If you did not get that answer, but your method was wrong, just go through my thought process and try to make sense of why I chose the strategy that I did to solve this problem. So here's the second part of the question, which is, what is the maximum speed of the box? Okay, and so that question requires some recall of the ideas related to simple harmonic motion, which is that I know that the maximum speed happens when all of the energy has been converted into kinetic energy, all of the elastic potential energy, that is. So if I'm looking at the equation for the total energy, let me write some of this out, right? Then I'm looking at taking all of my elastic potential energy that I might be storing and then converting that into kinetic energy at the end, right? So let's write some of that out. I have my kx squared over 2. And all of that elastic potential energy is going to be transported into, or transformed rather, into kinetic energy. And so in this case, again, I see that I have those halves that I can get rid of. I have all of the other information to solve this problem. I have my spring constant, spring force constant. I know that I've compressed it by 8.6 centimeters. I know that all of that 8.6 centimeters worth of displacement is going to help me get enough elastic potential energy to create that maximum velocity. So now it's just a matter of me substituting in the values that I know for this problem. Let me do that. So I have 24 newtons per meter times my 0.086 squared. Let me create a little bit more space here. And that has to be equal to my mass, which was the 0.055 kilograms, times my v squared. And so solving for v, I end up getting a velocity of 1.8 meters per second. So hopefully you found this to be not too challenging of a problem to solve. I have highlighted some homework questions here for you to work through to help make sense of these ideas. But more importantly, I want you to do some additional reading on your own, and it's this stuff right here. Okay, I want you to read a little bit about damped harmonic motion. And damped harmonic motion occurs where you do not have a frictionless system. But I do want you to do a little bit of reading about where that applies, why we care about it, and why we need to be concerned about its effect on simple harmonic motion. So that's it. Remember that you do have a quiz on the energy chapter on Tuesday's class. So if you have any questions in the meantime, make sure that you find a way to get in touch with me so we can work out any of the questions that you have.